Today we'll be covering Leetcode 98, validate binary search tree. Our first example has a node with value 2, node.left value of 1, and node.right value of 3. The definition of a binary search tree is a tree where all node values in the left subtree are less than the current node value, and all node values in the right subtree are greater than the current node value. Looking at our example tree, we can see that node.left is 1 and is less than node.val, and node.right is 3, which is greater than node.val. So we would return true. This binary search tree is valid. Okay, so let's dive into another illustration so that we can work our way towards actually writing our code. So let's have a new tree. We'll have 5, and then maybe 3 and 8. And then here we'll have, let's say 1 and 4. And now I'm intentionally making this a valid binary search tree. That's what I want to do this example on. And so on this side, let's make it just a little bit more interesting than the left one. We will put a 7 here. And then maybe on this side, we'll do a 2. Okay, so this is our valid binary search tree. Now we're going to do a recursive DFS call. So we're going to need a base case. So what are we going to use for that base case? Well, as is the case with most of these tree problems, it'll be if not node return true. And I'm just writing in shorthand for now. These are just notes. So think about the structure of each of these nodes. The tree node has 3 properties: self.val, self.left, and self.right, where the value is an integer and left is another tree node and right is also a tree node. So think about down here, when we get to 2, what are left and right? Well, they're none. And then here, the left node here is none. Left and right here, none, none. Left and right here, none, none. And the right node here is none. And that's why we're using if not node return true. Because if there are no values, then the right value can't be less than, and the left value can't be greater than the current value. So this is a valid binary search tree, and we're going to return true from there. So now let's think about how we could determine if we're out of bounds. Now we could say, let's compare at each level, right? Let's compare 5 to 3, and then 3 to 1, and then 1 to 2. But I'm sure you can see how this would be maybe less than ideal. We could probably do an iterative approach with a stack. I'm just choosing not to do that. In this instance, we're going to use DFS and we're going to use recursion. And the way I like best that I've seen this done is we're going to use left and right boundaries. So let's copy the root node and let's think, what is the right boundary? What's the highest number we could hit and still be valid? Infinity. There is no right boundary. And on the left, how low can we go? Negative infinity. Okay, so let's start building our DFS function down here. So DFS, we're going to pass in a node, and then we're going to have a left boundary and a right boundary. So for this first value, the right boundary is infinity, the left boundary is negative infinity. So in our last tree, we went from 5 to 3. So let's think about the DFS call on 3. So this is the left child of 5. So it must be less than 5. So when we call DFS, let's not write it down here in the definition, but when we call DFS on 3, when we call it, so we're going to pass in our node. What is our left boundary? It's still negative infinity, right? That didn't change. But what's our right boundary? 5, which is node.value. So looking from the perspective where this is our current node, when we call DFS, we're going to call DFS on node.left. And then the left boundary is going to remain the same. And the right boundary becomes node.value. Now let's look at it on the right side. I believe we had 8. So when we call DFS on the right subtree, we're calling it on node.right. And our left boundary is node.value. And our right boundary remains the same. So these are going to be our recursive calls inside of this function. But we need to check a couple of things before we get to that recursive function. So we already know our base case. So if not node, let's put in one line to save space, return true because my handwriting is giant. Now we need to check if we're out of bounds. So if node.value is less than, if it is less than the boundary that we have set. So let's look back at our recursive call here. So node.left, the left boundary remains the same. And then the right boundary becomes node.value. So let's think about this. If node.value is the boundary, yes, we don't want to be less than or greater than, depending on which side we're going to, but we also don't want to be equal to it. So if node.value is less than or equal to left, or our logical or, if node.value is greater than or equal to right, we're going to return false. Because that means we're out of bounds. So if we have a right subchild, the right boundary is 5. Well, if it's 5, invalid. If it's 6, invalid. Lastly, we're going to do our recursive call. Now, think about it. We just did an or here, because if either one of these is false, we got to return false and break the recursion. But what's it going to be when we call it on the left and right subtree? This is only a valid binary search tree if this is a valid binary search tree and this is a valid binary search tree. So in our recursive call, we're going to return DFS on node.left. I'm just copying this from here. Left and node.value with a logical and of DFS on node.right, node.value, and right. That's going to be our recursive call. We want the logical and. It's all or nothing. If they're both true, then it's a valid binary search tree. So outside of the function, right, we have our whatever is valid binary search tree, whatever Leetcode gives us, or whatever we want to call it. The way we're going to call this is we're going to call return DFS. And you remember, so we're going to call it on a root. And you remember what our boundaries were? So the way to do this in Python, it's pretty simple. So float of negative inf for infinity and float of inf. And it barely fit it on there. And then we're going to go ahead and go to the IDE and write some code, submit it, see how we do. Okay, so here we go. Let's start writing some code. So we're going to have to create our DFS function. So def DFS. Remember, it's going to take 3 parameters. We're going to have a node, a left boundary, and a right boundary. First thing we're going to check is our base case, if not node. Once again, that is the instance for a lot of these tree problems. We're going to return true. If we get past that, what we're going to check is if we're in bounds or out of bounds. So if node.value, or they call it val, is less than or equal to left, or node.val is greater than or equal to right, then we're going to return false. Lastly, remember we're going to do our logical AND. So we're going to return DFS on the left subtree, which is going to be node.left. The left boundary remains the same, and the right boundary becomes node.value. As we can see in the problem we did here, so if we're running it on 5, the right boundary is infinity, left boundary is negative infinity. If we call it on node.left, left boundary remains the same. It remains negative infinity. But the right boundary becomes node.value, 5. So we're going to do the logical AND with DFS on the right subtree. So node.right. And this time, the left boundary gets updated to node.val, and the right boundary remains the same. So if we're calling the recursive call from here, the subtree is going to be node.right, where the right boundary is still infinity, but the left boundary becomes node.val. Now, let's see, I might have to grow this a little bit. I don't know that Python would like that empty space. So we've got that. Now we need to call our DFS. So we're going to return DFS, and the initial call is going to be on root, with the left boundary being float, remember, negative infinity, and the right boundary is going to be float infinity. Now let's go ahead and we're going to run this and submit. And as we can see, Leetcode is very happy with that submission. Let's walk through it once with our example, just so we can see what's going on. So our initial call on the root has a left boundary of negative infinity and a right boundary of infinity. So if not node, that's not the case. Now we're going to check the value. Is it out of bounds? Is it less than left or greater than right? No, it is not. So we're going to do our recursive call. We're going to go to 3 and 8. So the left boundary is negative infinity, and the right boundary is 5. Left boundary of 8 is 5, right boundary is infinity. Are these out of bounds? No. Then we're going to do our recursive call. So negative infinity, 3, and this right here is still going to be 5, and this is going to be positive infinity. When we get to the call for here, this returns true. Down here we got true, 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 and true. And so that's at the top of our stack. We have all trues. So this logical AND evaluates to true, and we get to return true, and we're done.